All right, so are you ready to dive deep? Today we're tackling flow control scaling in PCIe.
Ooh, that's a good one.
You're here because you want to grasp how data fly through your computer without, causing a total system meltdown.
Yeah.
Think of it as, designing the traffic system for a super fast city of the future. Our goal, no gridlock.
That's a fantastic analogy. PCIe, or Peripheral Component Interconnect Express, it's basically the highway system inside your computer.
Right?
And with each new generation of PCIe, we're pushing those data speeds faster and faster.
Oh, for sure.
But without flow control, it would just be utter chaos.
Okay, so flow control's like the traffic cop. Make sure everything's running smoothly. But what's this scaling business all about?
Yeah, that's the key.
It can't be as simple as, stoplights and speed limits, right?
You're right. It's way more dynamic than that. Imagine if each lane on a highway had a fixed number of cars allowed at once.
Oh, okay.
That's how traditional flow control worked. And it was fine, for a while. But with high bandwidth devices like EPUs and SSDs, that system, it's just a bottleneck.
I see where you're going with this. So flow control scaling is more like a system that can, dynamically open up new lanes? Or maybe adjust speed limits based on what traffic is doing in real time.
Precisely. It's about making sure that one slow lane doesn't back up the whole highway.
Right.
Flow control scaling brings in this clever idea of a shared credit pool. It's like extra lanes that can be allocated to any lane that needs them.
So it's more like a smart highway system, adapting to conditions as they change. But what kind of performance gains are we talking about? Does this really make a difference that you notice?
Absolutely. In fact, studies have shown that flow control scaling can boost data throughput by 30%, especially for tasks that are really GPU heavy, like gaming or video editing.
Wow. 30%, that's huge.
Yeah, and it also helps to prevent those dreaded deadlock situations. That's where data transfer completely stalls out because of a bottleneck.
Oh yeah, like a total gridlock situation. So this isn't just about theoretical efficiency. It actually affects how well our computers perform.
Oh, absolutely.
Okay, I'm starting to see why this is such a big deal. But how does this shared credit system work? It sounds pretty complex.
It is complex, but the core concept is surprisingly intuitive. Let's break it down. In the traditional credit-based system, each lane or virtual channel, we call them VCs, has a fixed number of credits.
Okay.
And these credits are like permission slips to send data. As data packets are sent, credits are used up, and the receiver replenishes them as it processes the data.
So each VC is it's like it has a prepaid data plan, but with a limited balance.
Right. But with flow control scaling, you have this central reserve of credits that any VC can tap into if needed.
Oh, okay.
This allows for much more flexibility, and it prevents one slow VC from holding back all the others.
So instead of fixed data plans, we have this system where VCs can sort of borrow data from a central pool. That's pretty clever. But wouldn't managing this shared pool add, a ton of overhead?
It does add some overhead, but the benefits really outweigh those costs. And keep in mind that engineers are always working on optimizing these systems.
Right.
For example, scaled flow control credits.
Okay.
They allow for a much finer-grained adjustment of credits.
Oh, interesting.
Using smaller units, which helps to reduce that overhead and improves efficiency.
Scale flow control credit. So can you unpack that a little bit? Is it literally a dimmer switch for data flow?
Yeah, that's a good analogy. Basically, instead of allocating credits in big chunks, the system can adjust them in smaller steps, which results in smoother, more responsive flow.
Okay.
Think of it as being able to adjust the width of the lane on our highway to, accommodate different types of vehicles.
That makes sense. So we've got our VCs, we've got our shared credit pool, and then these scaled flow control credits. It's starting to feel like we're building a pretty sophisticated traffic management system here.
We are.
But I'm curious, what are some real-world examples where this is crucial? Does this actually affect me as a user?
Oh, absolutely. Think about gaming PCs with powerful GPUs.
Okay.
They really rely on flow control scaling to keep the data flowing smoothly between the GPU and everything else. Without it, you would experience lag, stuttering, maybe even crashes during graphically intense games.
So that's why my games run so smoothly. I never realized how much was going on behind the scenes to keep everything in sync. What about other examples? Does this apply to things like data centers?
Absolutely. Imagine the massive amount of data flowing in a data center. Flow control scaling is essential for maintaining efficiency and preventing bottlenecks in those environments.
Yeah, that makes sense. I'm starting to see how this is applicable to so many areas. But let's bring it back to a more concrete example. You mentioned something called the Versal Adaptive SoC earlier. Can you tell us a bit more about that?
Sure. The Versal Adaptive SoC is a great example of a real-world implementation of flow control scaling. It uses this technology to manage data flow for a whole bunch of tasks, including high-speed networking and data processing.
So it's like a real-world example of our smart highway system in action.
Precisely. It shows how flow control scaling is being used in cutting-edge technology to handle the demands of modern computing.
Okay, I'm really starting to get the big picture. Flow control scaling is like the unsung hero of data transfer, working behind the scenes to make sure everything's running smoothly and efficiently.
Well said. It's definitely a critical piece of modern computing, and as data rates continue to increase, it'll only become more and more important.
This is fascinating stuff. But I'm wondering, if flow control scaling is so great, are there any downsides? Nothing is perfect, right?
That's true, there are always trade-offs. One of the biggest challenges is the complexity of actually designing and implementing these systems. It takes a lot of planning and engineering to make sure it all works correctly.
I can imagine. It's like designing a highway system for a city that's constantly growing and changing, right? Are there any other limitations?
Well, there's always some overhead associated with managing the shared credit pool and making all those adjustments on the fly, but engineers are always working on minimizing that overhead with clever algorithms and hardware optimizations.
So it's this balancing act between complexity and efficiency. But overall, it seems like the benefits of flow control scaling really outweigh the costs.
Absolutely, especially in the world of high-performance computing we live in today, where speed and efficiency are everything.
All right, I think we've laid a good foundation here, understanding what PCIe and flow control are and why this scaling aspect is so important. But I'm ready to dive deeper into the specifics.
Let's do. We can unpack the details and really get into the nuts and bolts of how it's implemented.
Sounds good. I'm ready to go even deeper into the world of flow control scaling.
Awesome. It's kind of fascinating, to think about how flow control has evolved along with the growing complexity of our computing systems.
Yeah.
It's almost like we're mirroring the challenges of urban planning, but in the digital world.
That's a cool way to look at it. And speaking of evolution, you mentioned before that traditional flow control was kind of like a basic highway system with fixed lanes.
Right.
Can you break down how that system worked, in a little more detail?
Sure. Imagine a highway with multiple lanes, each one representing a virtual channel or VC.
Okay.
In the old system, each VC had its own dedicated buffer, like a little parking lot, and a fixed number of credits. These acted as entry tickets for those data packets.
Okay.
The transmitter could only send a packet if it had a credit, and the receiver would issue more credits as it processed the data.
So it's kind of like a toll booth system, where each lane gets a limited number of passes?
Exactly. This worked well for simpler systems where the data flow was pretty predictable.
Yeah.
But as we started pushing those data transfer speeds, with things like high-def video and 3D gaming,
Right.
that fixed lane system, well, it started to cause some traffic jams.
I could see how that'd be a problem. If one lane gets backed up, it slows down the entire highway.
Exactly. And that's a big limitation of the traditional flow control, you see. It's just not very adaptable to changing traffic conditions.
So that's where flow control scaling steps in. With its more dynamic approach, we talked about the shared credit pool, but I'm still a little fuzzy on how it actually works in practice. Can you give me a specific example?
Of course. Let's say you're editing a 4K video, which involves moving huge amounts of data between your storage drive, your system memory, and a GPU.
Okay.
With traditional flow control, each of those components would have its own fixed allocation of credits and buffer space.
Right.
Now, if one of them, say your storage drive, suddenly has to send a large burst of data, it'd quickly use up all its credits and have to wait for the receiver to send more, creating a bottleneck.
Oh, so it's like a traffic jam on the on-ramp to the graphics card, even though the highway's mostly empty.
Exactly. But with flow control scaling, that storage drive, it can borrow credits from the shared pool,
Oh, okay.
allowing it to just keep sending data without that interruption. Meanwhile, the system is monitoring traffic across all those VCs and dynamically adjusting the credit allocation to keep things flowing smoothly.
So it's like having a smart traffic management system that can open up new lanes or reroute traffic to less congested routes in real time?
Exactly. That ability to adapt, that's what makes flow control scaling so powerful. It makes sure every component gets the resources it needs when it needs them without creating those bottlenecks.
Makes sense. So just to recap, traditional flow control is like a highway with fixed lanes and not much adaptability.
Right.
Flow control scaling, on the other hand, is like a smart highway that can adjust lane configurations, dynamically and fine-tune the traffic flow based on changing conditions.
You got it. And it's that shift to a more dynamic and intelligent system that really lets modern computers handle the massive data demands of, everything we do today.
Yeah, it's cool to think about how these concepts from the real world, like traffic management, are being applied to the digital world.
It really is. It's a great example of how engineers, they get inspired by the world around them to solve complex problems.
Absolutely. So we've talked about the high-level concepts, but I'd love to dig a bit deeper into the mechanics of it. How is flow control scaling actually implemented? What are the key bits that make it all work?
Well, one crucial element is this idea of virtual channel, or VC, management.
Okay,
Remember, VCs are like the individual lanes on our highway analogy, each carrying data between different parts of your computer.
right.
Flow control scaling needs a really sophisticated system to manage those VCs effectively.
Right. So it's not just about like having the shared credit pool. It's about how those credits are distributed and managed across all the different VCs.
Precisely. VC management, it involves several key functions.
Okay.
Things like credit allocation,
Okay.
credit replenishment,
Uh-huh.
and traffic monitoring.
Okay, cool. So let's break those down one by one. First, credit allocation. How does the system decide how many credits each VC should get, both from its own pool and from the shared one?
That's where it gets really interesting. There's no like one-size-fits-all approach.
Yeah.
The strategy can change depending on the implementation and what performance goals you're after.
Right.
But some common ways to do it include, priority-based allocation,
Okay.
where VCs carrying, say, high-priority traffic are given more credits. And then there's demand-based allocation,
Okay.
where credits are given out based on the current needs of each VC. And lastly, there's fairness-based allocation,
Okay.
which tries to distribute credits evenly to prevent any one VC from hogging all the resources.
So it's like having a system that can prioritize certain lanes based on like the type of vehicles and how urgently they need to get through.
Exactly. And that credit allocation mechanism, it's constantly evaluating all these factors and making adjustments to make sure the flow is optimal.
Okay, that makes sense. So once the credits are allocated, how does the system make sure they get replenished in time?
That's the job of the credit replenishment mechanism. As the receiver processes those data packets, it needs to replenish the credits so the transmitters can keep sending data without interruption.
Right.
This usually happens in the background and is handled by the PCIe controller, which is a specialized chip that manages that PCIe link.
So it's like having automated toll booths that issues new passes as cars exit the highway?
Precisely, and how efficient that replenishment process is, it's really crucial for maintaining that smooth flow of data.
Yeah, that makes sense. So we've got credit allocation and replenishment. What about traffic monitoring? You mentioned that before as a key function of VC management.
Right. To make good decisions about, credit allocation and other tweaks, the system needs to constantly keep an eye on the traffic patterns on each VC.
Right.
That means tracking things like the number of packets being sent, the rate at which credits are being used, and any signs of congestion or potential bottlenecks.
So it's like having traffic cameras and sensors all over that highway collecting data on how fast traffic is moving.
Exactly, and that data gets fed into those credit allocation and other management algorithms to fine-tune things and optimize the flow.
Wow, this is starting to sound like a really sophisticated traffic management system.
It really is, and it's only getting more complex as data rates keep going up and the demands on our systems keep growing.
I'm starting to really appreciate how intricate it all is, all those algorithms and hardware working together to make this happen seamlessly. It's like a hidden world of data traffic management.
It is, and it's a real testament to how clever the engineers are who design these systems. They're basically creating the traffic infrastructure for the digital age.
That's a cool way to put it. So we've covered VC management with credit allocation, replenishment, and traffic monitoring. What about the shared credit pool itself? How's that actually implemented?
Usually, the shared pool is implemented as a dedicated block of memory within that PCIe controller. The size of it can vary depending on the implementation and the bandwidth requirements of the system.
So it's like having a reserve fund for data transfer ready to go wherever it's needed most.
Exactly. And those management algorithms we were talking about, they determine how those reserve credits are allocated and spread out among those VCs.
Gotcha. This is all making a lot more sense. But I have to ask, are there any real-world examples of flow control scaling in action?
Oh, absolutely. Actually, it's becoming more and more common in modern computers, especially ones that handle high bandwidth data, like, for example, high-end GPUs, the kind you see in gaming rigs or video editing setups.
Right.
They depend on flow control scaling to keep the data moving smoothly between that GPU and the rest of the system.
Ah, so that's why my games run so well. I never realized such a complex system was working in the background to keep all those pixels flowing. What about other examples? Does this apply to data centers as well?
For sure. Think about the huge amounts of data moving around in a data center. Flow control scaling is essential for keeping things efficient and preventing those bottlenecks in those really complex environments.
So it's like a super efficient traffic system for an entire city of data.
Precisely. And as data rates go up and new technologies come out, we can expect flow control scaling to be even more important in the future of computing.
Yeah, I bet. This is all really fascinating. But I'm also realizing that this level of complexity probably comes with some challenges. Are there any downsides or limitations to flow control scaling that we should be aware of?
You're right, no technology is perfect. One of the main challenges is just how complex it is to design and build these systems. Managing that shared credit pool, dynamically allocating those credits and buffers, monitoring the traffic patterns, it all requires pretty sophisticated algorithms and hardware.
I can only imagine. It's like trying to design a traffic management system for a city that's constantly growing and changing. You'd need a team of the best engineers in the world to make that work flawlessly.
Exactly, and that's why it's crucial to have really skilled engineers and strong design methods to make sure that those flow control scaling systems are implemented right and run reliably.
So complexity is one challenge. Are there any other limitations we should know about?
Well, there's always some overhead, right? All that managing and adjusting requires processing power and bandwidth. It's like having a bunch of traffic controllers constantly watching and adjusting the flow of data, and they need resources to do their jobs.
Right, so it's a balancing act between the efficiency gains of flow control scaling and the resources needed to manage it all.
Exactly, and that's a key thing for engineers to consider. They're always trying to find ways to minimize that overhead through clever algorithms and hardware optimization, efficient design techniques.
It's like trying to design a traffic management system that's both effective and energy efficient.
That's a great analogy. And that's the essence of good engineering, finding the right balance between all the priorities.
Totally. Well, despite those challenges, it's pretty clear that flow control scaling is essential for modern computing. It's letting us push those data transfer speeds and handle all those massive data demands from, well, everything we do these days.
I completely agree. And as we move toward even faster data rates and even more complex system, flow control scaling is going to become even more important. It's a technology that's, it's shaping the future of how we interact with data.
Yeah, this has been a really insightful deep dive into the world of flow control scaling. We've gone from the basic ideas of the old way of doing things to the complexities of dynamic credit allocation and VC management.
Yeah, and we've only just scratched the surface. There's still so much more to explore.
Speaking of exploring, I'm really curious to learn more about, the future of flow control scaling. What kind of advancements are on the horizon?
That's a great question, and it's a topic that's full of possibilities. Let's jump into the future of flow control scaling and see what's in store for this, this game-changing technology.
It's amazing to think that all this complex data management is happening. Every time we use our computers, it's like a whole hidden world that we never see.
It really is. And, as we demand more from our devices, higher resolutions, faster speeds, more demanding applications, the challenges of flow control, they just get tougher.
Right. We've talked about how flow control scaling is already being used in things like GPUs and data centers. But what about the future of this tech? What's next for data transfer efficiency?
Well, one thing that's getting a lot of attention is reducing overhead.
Okay.
We talked about how managing the shared credit pool and dynamically adjusting allocations, well, it takes processing power and bandwidth. Researchers are always trying to make these processes more efficient.
So it's like optimizing that traffic management system, right? Making it leaner and faster so it doesn't slow down the whole network.
Exactly. One way is to develop smarter algorithms that can make better decisions about credit allocation and buffer management. Another is to look at new hardware implementations that can handle these tasks more efficiently.
So it's like upgrading the traffic control centers with faster processors and better communication links, right? So they can respond to those changing conditions more quickly.
Yeah, that's a great way to think about it. And, as chip design technology improves, we're going to see even more innovative hardware solutions that push the limits of flow control efficiency.
Okay, reducing overhead is one thing. What else is on the horizon for flow control scaling?
Another important focus is, improving quality of service, or QoS.
Oh, okay.
As data traffic gets more diverse and demanding, with all that real-time streaming, high-priority transactions, and less time-sensitive stuff mixed in, flow control scaling has to be able to prioritize that traffic effectively.
Right, so it's like having a system that can intelligently prioritize ambulances and fire trucks over regular traffic, right? Making sure that the most important data gets through fast.
Exactly. And this means developing, more advanced QoS algorithms and prioritization schemes that can take into account the needs of those different types of data traffic.
It's really interesting to think that we're basically creating digital traffic laws to manage that flow of data.
Yeah, and as data becomes more and more important in our lives, those laws will only become more crucial.
For sure. Now, I've heard a little bit about the potential for artificial intelligence and machine learning to play a role in flow control scaling. Is there anything to that?
Oh, yeah, there's definitely a lot of excitement about that possibility. Imagine a system that could actually learn from past traffic patterns and, predict future demands, and then proactively adjust those credit and buffer allocations to avoid bottlenecks before they even happen.
That's like a traffic management system that can predict rush hour, right? And adjust those lane configurations in advance to keep everything moving smoothly.
Exactly. And that's what's so powerful about AI and machine learning. They can analyze those massive amounts of data and, identify those patterns and make those predictions that can help us optimize these complex systems.
That sounds incredibly futuristic, but also a little bit scary. Do you really think we're close to seeing AI-powered flow control?
It's definitely something that people are actively researching, and there are already some really cool developments. For example, some folks are looking at using reinforcement learning, a type of machine learning, to train these systems to adapt to changing traffic patterns and make good decisions in real time.
Oh, okay. So it's like giving the traffic management system a mind of its own so it can, like, learn and adapt without us having to step in.
Yeah, that's the goal. It's still pretty early, but the potential is huge.
It's wild to think about how far we've come with managing data flow. From those, early systems with fixed lines to the smart dynamic systems we have now, and then the possibility of, like, AI-powered flow control. It's amazing what we can do.
I totally agree. And I think that's a great point to end all. Flow control scaling isn't just a technical thing. It's a great example of how we're always pushing those boundaries in the digital world.
Definitely. And it shows just how crucial it is to have efficient data management for our devices and systems to work well.
Well said. It's a reminder that, even though we don't see it, there's a lot of complexity working behind the scenes to keep everything running smoothly.
Well, this has been a really mind-blowing exploration of flow control scaling. We went from the basics to the cutting edge, and even got a glimpse of what the future might hold.
It's been a lot of fun.
So to our listeners, we encourage you to stay curious, keep learning, and, never stop asking those questions. The future of tech is in your hands.
Thanks for tuning in to this deep dive.
We'll catch you next time with another exciting look at the world of technology. Until then, keep exploring. 30 seconds.